So question 3 of quiz 1 was find the expectation value of the Hamiltonian for various determinants. The first one was psi 1, psi 2. Then there was psi 1, psi 2 bar. Then psi 1 bar. So let's do the first 3. So what you had to do basically was, since these are two different spatial orbitals, you draw the two energy levels. Okay, this is psi 1, this is psi 2. Then here you have two alpha electrons. So you have an alpha electron in psi 1, alpha electron in psi 2. In the second one, you have an alpha in psi 1 and a beta in psi 2. And again here you have a alpha in psi 1 and a beta in psi 2. So this is what is called an occupation diagram. You just put the electrons in the orbitals. Okay. Then you want to write the energy. So the only information that you need here is that the exchange is considered only for electrons of same spin. So in the first case, you have the one electron term for each electron. So that is H11 plus H22. And then you have the Coulomb repulsion between them, which is J12. And since they are of the same spin, you can exchange them. So you have minus K12. Simple enough. In the second case, again, the one electron terms are the same. So H11 plus H22. The Coulomb is again also same, J12. But since they are of opposite spin, you don't have an exchange. In the third case, again, there is H11. But the second electron is also in psi 1. So you have 2H11. Then you have the Coulomb repulsion between the two electrons in 1. So J11. And they are of opposite spin, so no exchange. Is that clear to you now? It's pretty simple. You just need to do it like this. This is actually very similar to Szabo-Ostrand exercise 2.23. So if you had read the book, then you would have already encountered the occupation diagrams. Fine. Is it clear to everyone now? Does someone have a doubt still?
Yes, ma'am. Thank you.
Okay.
Ma'am, for the psi 3 case, so there would be 1, 3, 2, 3 terms.
Yes, if you like, I can do one of them also. So if you have
But in the question, the Hamiltonian part of the exchange integrals or Coulomb integrals, there is no 3 terms there.
Oh, but I said etc. I mean, analogous
Oh,
terms
okay.
you can always write.
Actually, that part I get confused. Okay.
Oh, you got confused by that, and you know what you all should have done? You all should have WhatsApped me at that point, saying, "Ma'am, what is an occupation diagram?"
Yes, ma'am. I think I have messaged you in the group that time, but
You did
you
mention,
give.
but I only saw them. I saw the messages. They came maybe 2-3 minutes before the close of the quiz.
Ma'am, I messaged you at around 4:32 p.m. that what is an occupation diagram in the
You
group.
did.
Yes, ma'am.
You did. I was sitting with my phone, but I did not see it. Okay. Then sorry. Then I'm so sorry. But it was strange that only one of you actually managed to do it, and some of you have evaluated them algebraically, but that will take much longer. So drawing the diagram and using this kind of analysis is much quicker. Anyway, this was the first quiz. We will make up all this later. It will be fine. Don't worry. And the other questions, they were fine. I think most of you got them right. So the
Ma'am,
quiz was
hold on, okay, I'll tell later.
No, you can ask, no problem.
Ma'am, in assignment, like in question number 2, This
Yeah.
said like draw the molecular orbital diagram for LIH, lithium.
Yes.
Molecular orbital diagram means like similar to this, like what you are showing, like straight line. Then I will fill up with electrons.
No, actually, when I say occupation diagram, then it is simple. Molecular orbital is a little bit more. So, an MO diagram, you have to start with the atomic orbitals. So, you have, let's say, Li and H, like here. Then you draw the 1s and 2s. Okay, and hydrogen 1s. I'm already showing you half the things, and then you show the then you fill them. So you fill the atomic orbitals with energy. So Li is 3 electrons. Okay, hydrogen is 1 electron, and then you show the uh, interactions to give the various energy levels. I'm not doing the full thing. You can always Google this. Okay, it's
No,
not
I did
required.
like in YouTube. So what they are showing is like they're splitting the oneness orbital in like some sigma and pi.
Yeah. So once they interact, then the molecular orbitals are labeled by their symmetry. So the atomic ones are simply called 1s, 2s, 2p, like you normally do. And then you have 1 sigma star. This, some people write it like this. Okay, then 2 sigma star. Okay. This is the labeling of the molecular orbitals according to their symmetry.
Okay,
How come
and
you have not done this? I mean, this
ma'am,
is
I haven't done the sigma and pi thing, ma'am. Like
okay.
so, uh,
You know what? So when you have a sigma orbital, that is basically symmetric around the bond axis. So things which look like, so if you have an Li here and an H here, then an orbital which looks like this, it is symmetric about the bond axis. Those are the sigma orbitals. Okay. Oh, so if you all don't know MO theory, then I have to like take a full class on it. It is not easy to just say it like, I mean, you will not understand properly. Then if you have something like this,
Madam, full class is necessary.
yeah, I think a full class is necessary for the MO diagrams. Okay, okay. Let's see, maybe I will ask Vivek to take a class on the MO diagrams. Okay? And then the physicist can attend and the chemist can take a break. Okay?
okay, ma'am.
So I will ask him to do it. So if you all can't answer question 2 properly now, then let it be. I will extend the deadline for 1 more week. Okay?
That would be good, madam.
Okay, okay. Now, if you don't know it, there is no point in copying from Google or wherever. Then you will not learn anything. So I
Ma'am, I can
will.
do like in question number 2, but it will be wrong.
Yeah, don't do it. I will extend the deadline for 1 more week. We'll have a class on the MO theory. I'll ask Vivek. If not, I will take it and take the class, and then we will. Then you can submit the assignment properly. Okay. And those who have already done it, the chemists, they can submit it if they like. That's fine also. Okay.
No, first 2 question already solved, but last question.
Yeah, but I clearly remember I learned doing this in class 11 or 12. Okay. Anyway, if you have forgotten, no problem. We will do it again. But today, let me just finish Hartree-Fock. Then I can give you the Hartree-Fock assignment as well. Let me finish with what I wanted to finish. Okay. So, fine. So last class, we kind of summarized the Hartree-Fock procedure and we talked about the full algorithm. But there are some little things that we still need to think about. And since the Hartree-Fock theory has a lot of steps, I will also summarize the steps so that it's clear to you which step does what. Okay. So first, let us do the summary then. Summary of Hartree-Fock theory. So the first thing about Hartree-Fock theory is that it approximates the wave function as a single determinant. Okay, psi is a single determinant, and then it uses the variation principle variational principle to get the single determinant which gives me lowest energy for the Born Oppenheimer approximated molecular Hamiltonian. So someone tell me, what is the Born Oppenheimer approximation? Who remembers?
Like electrons are very fast moving compared to that, like the nucleus can be considered that they are at rest.
Yeah, you consider them at rest. So the nuclei don't move while the electrons move. So we can have a description for the electrons independent of the position of the nuclei. Right. That is the Born-Oppenheimer approximation. Okay. And then we have the molecular Hamiltonian, which is different for different molecules. So which terms in the Hamiltonian are different for different molecules?
Ma'am, the nuclear part.
The
Nucleus
nucleus
and
electron attraction.
interaction.
Yes. Yes.
The remaining is the same.
The remaining terms are the same. Just the rest of it depends on the number of electrons. So for various molecules, you only have one thing different. Only the nucleus electron attraction term is actually different. This is one way in which it's different, and B is the number of electrons. But overall, when you optimize the wave function, since the energy is a balance of all the terms, the wave functions turn out to be very different. Anyway, so we had a single determinant, and we say that we find the single determinant with the lowest energy. But does this optimized determinant, or let's say, is this optimized determinant an eigenvector for some Hamiltonian? So this is a question we will answer today. So we have obtained the determinant by variational optimization. So it is not an eigenvector of the full Hamiltonian. That is clear. But is it an eigenvector of some approximate Hamiltonian? So that we will have to look at. Then once you have so what is the equation that you get from the variational principle? That is the Fock operator equation, which gives me the various spin orbitals. No, this is AB epsilon. Was it? Yeah, it was AB. IA. So this is what we get from the variational principle. Then we do something more. So this was the differential equation that we get. Then we say that I represent each spin orbital, chi A as a linear combination of atomic orbitals, or equivalently expand in a basis. And after we do that, we take matrix elements with respect to this basis. Let's say we call this phi mu. And then we obtain a matrix element, matrix equation F mu nu, some let's say A, C, one second. Yeah. So I cannot, I have to write this. Sorry, I cannot write this like this. I will write it properly. K is number of basis functions. So there is a big difference between this equation 1 and this equation 2. So from equation 1, we had identified epsilon, the diagonals of epsilon AB as the energies of the spin orbitals. And these spin orbitals are the orbitals of the molecule. So they are what are called molecular orbitals. Here, mu and nu are atomic orbital labels. Okay. So these, so a projection of, let's say, chi B F chi A equals to epsilon this will be epsilon AB delta AB. So the diagonals would be energies of the orbitals. So, and this was also called an FBA or something. So FBA and F mu nu, they are different. FBA is in the molecular orbital basis. So their expectations of the Fock operator with respect to the molecular orbitals. The Fock matrix, as it is called, capital F mu nu, this is the elements of the Fock operator in the basis function. So the energies that are associated with a mu or a nu, they don't appear in the equation. They don't mean anything. So this epsilon I is still the energy of the molecular orbital chi I. So don't get confused between these two equations. So once you expand the spin orbitals in a basis, the matrices involved like Fock and overlap, they are expectation values of the operators in the basis. Okay. but you never, but the energies of these atomic orbitals per se don't appear in any equation. This equation, the energies are always of the molecular orbital. So that is one thing I wanted to clarify today. So these two, so sometimes you will see FBA is called a Fock matrix, and sometimes F mu nu is called the Fock matrix. You have to be always careful about which Fock matrix is being talked about. Okay. In the actual computation, your F mu nu will be an input. So that is what you need to compute before starting the computation. And once you get your spin orbitals, then you can construct FBA. Okay. And often in post-Hartree-Fock methods, like when you include correlation, then you will use the FBA. So in the molecular orbital basis, and that will be called the Fock matrix in the post-Hartree-Fock method. Then that is an input for the post-Hartree-Fock methods, but for the Hartree-Fock it is the output. So just be clear about that. So this was the equation that we obtained, and then in shorthand notation this was Fc equal to SCE, which is called the Rotan equation. But we still do not know how to solve it. So in order to convert that into an eigenvalue equation, we use either symmetric orthogonalization or canonical orthogonalization. You can use either, but the canonical orthogonalization is what is used. And what is that? That is, you define a transformation X which acts on or you define a new set of coefficients from the old set of coefficients, which gives you a diagonal which gives you a diagonal overlap. So we want to so if you have FC equal to SCE, you want to convert it to FC prime equal to C prime epsilon, which will be my eigenvalue equation. And you want to choose an X which allows me to do this. So for symmetric orthogonalization, your X would have been simply S to the power minus half. And for canonical, X is equal to the eigenvalue is small s to the power minus half U. And how will we choose U? U is the diagonalizing matrix of S. Is this part clear to everyone? The part about how to go from Fc equal to SCE to Fc prime equal to C prime epsilon?
Yes, ma'am.
Yeah, this is clear? Okay.
Ma'am,
Yeah?
previously you mentioned something self-consistent field equation. What do you mean by that?
Yeah, I will come to that again. So now that this is converted to an eigenvalue equation, you can simply diagonalize the Fock matrix and get C prime. But this is not a one-step process. This is not a one-step process. And why is that? That is because my F mu nu contains the contains Coulomb and exchange integrals, which depends upon the C values, which contains C. So once you get C prime, you need to back calculate to get C and then construct a new F mu nu. So here the operator, the matrix form of the operator, it depends upon the eigenvectors of the equation. So it depends on the solution of the equation. So that is why this is called a pseudo eigenvalue equation. Because the matrix depends on its own eigenvectors. So you can't. So one diagonalization is not enough to solve it. So what is the process? You get C prime, you back calculate C, you reconstruct F mu nu, and you again diagonalize it. And you keep doing this till your C primes don't change any further up to a threshold. And that is why it is called a self-consistent field equation. So the Fock matrix, so there is a Coulomb field and an exchange field in the Fock operator. So that is a terminology. And this field is decided, or the value of this field is decided by the optimized orbitals in which the electrons are placed. So you find the orbitals and you construct the field, and you find the new orbitals and you construct the field till a point where you get an operator and a set of eigenvectors which don't change any further. So as you do this process, what will happen is that the values of the energies of the orbitals and hence the total energy of the system, the Hartree-Fock energy expression that we wrote, that energy will keep on reducing. So you get a lower and lower energy, which means that your determinant gets better and better. And once it is good enough, you stop. So that is why this is called a self-consistent field equation. Is this clear?
Yes, okay.
No, you don't sound very happy.
I mean, I will again listen in the recording.
Oh no, okay. I will give you like the short form. The short thing is that here the Fock matrix contains the eigenvectors. So it is not a one-shot procedure. So you guess that you have to first have a guess eigenvector, and then when you get the actual ones, you replace the guess with the actual ones, and then you repeat and you repeat and you repeat till the orbitals of the earlier step and the orbitals of the current step are not much different. So repeating it will not help you any further. And that is the point where you stop. Okay. So this is why it is an iterative procedure, and it is not just an eigenvalue equation. It is rather a pseudo eigenvalue equation. That is one point. The next point is, why is it a self-consistent field? Because this Fock operator, that is a one electron operator where the electron moves in a field of the other electrons. Okay. So and the other electrons, so how do you construct the field of the other electrons? You do it from the orbitals in which the other electrons are placed. And if these orbitals change, then the field changes. And when you're doing this iteration, the orbitals keep changing, right? So the field changes, still you attain a self-consistent field, which means that the eigenvectors that you get and the eigenvectors that you have used to construct the Fock operator, they are the same. So that is why it is called a self-consistent field. So the name comes after the requirement.
So we are taking the convergence of those eigenvectors.
Mm-hmm. Yes, exactly.
Yes, okay.
Yeah.
That's fine.
Yeah, you are taking convergence because the Fock operator, to construct this F matrix, you need C prime or the C's. That is why you need to do this. If F was, let's say, only the one electron part of the Hamiltonian, if it did not have the exchange integrals, then this would have been a one-step procedure. So like the non-interacting system that Professor Pal was talking about, then you don't need this iterative procedure. Then it is only one diagonalization. Okay. So, but here you have to repeat it. That is why. And instead of doing it directly with C, so a numerical let's see, I will put it in the same step, contains C. For numerical convenience, instead of writing the Fock matrix as a function of C, we write it as a function of P, where P is the density matrix. It is normally, you will just hear people referring to as the density matrix, but very specifically it is the charge density matrix. And P is basically C star C. This is the numerical convenience. Okay. So in the Hartree-Fock, in this chapter, for this theory, what I personally want you to understand most is why you are doing what. Okay. I will not ask you to derive something from something. So you don't have to learn up the steps in between. But you need to remember why which step is done. Because there are many, many steps. And why each step was necessary and why we do it. Okay, so this is this. So then you have the procedure, the self-consistent field procedure as such. And once you get the self-consistent solution, the converged spin orbitals, you calculate the Hartree-Fock energy. Can anyone tell me what the expression was for the Hartree-Fock energy? Who remembers? So it is a sum from 1 to n by 2 of the one electron integral. These are spatial integrals. Notice the n by 2. Then you have sum AB up to n by 2. This is a double sum. And you have 2 JAB minus KB. So this is the Hartree-Fock energy. Okay. So this is the energy of the full Hartree-Fock determinant. So while you are doing this procedure, the energies that you get, they are the energies of the individual spin orbitals. Okay. You are not getting the energy of the full determinant. Once you have reached the convergence, you can compute the full energy. You can also keep computing it at every iteration, and you will notice that with iteration, E0 becomes lower and lower till it converges. So now notice that there are two alternatives. So when you're judging the convergence, you can either see if the two possible criteria for, or let's say many possible criteria for judging convergence, say between iteration n and n plus 1, you can either see if if all the coefficients of n plus 1, so this is the full matrix C, if that is equal to Cn, this would be ideal, but this is a numerical procedure, it would never be exact. So what you do is this modulus of the difference of the coefficients between the two iterations once it is less than some threshold. This is one possibility. The second possibility is your energy. So you can see E0 n plus 1 minus E0 at n, if that is less than a threshold. And remember, we had introduced the density matrix as well. So you can do the density matrix of n plus 1 minus the density matrix of n if that is less than a threshold. And you can also think up other convergence criteria, but these are the most commonly used. But which is the best? Now, once you have alternatives, you have to do what is best, right? So what is best? So what you can show is that because this is a variational procedure, so this is a mathematical proof, I will not do it, but there is a theorem that for variational methods, the energies the error in the energy is quadratic if the while the energy in the coefficients error in the coefficients is linear, which means that if you have an error in the coefficient matrix of 10 to the power minus 2, then the error in E0 will be 10 to the power minus 4. So the energy will converge faster than the coefficients. Okay. So that means that the energy is less sensitive to the wave function. But if you want a correct wave function, and that is what you would like, because you will compute properties of the system by taking expectation values of the determinant for various operators, which may not be the Hamiltonian. So you want the coefficients to be correct. Okay. So this is the preferred method, either this one or this one. Now, this one is so this one, meaning the density difference in the density matrix, that is actually even more sensitive, or no, that is actually less, sorry, that is less sensitive than C. So if you manage to do C, you would get the best converged wave function. If you did the difference in the densities, that would be C star C, you would get a little worse. And if you just take the convergence with respect to energy, you would be less certain of your answer. However, you still have the threshold in your hand. So if you ensure that you take a very tight threshold for energy, then your coefficients will still be good enough. Okay. So when you code, this is the flexibility that you have, and you will find that different codes will adopt different methods. Some also adopt all three. So one by one. So first they see if the energy has converged, then they see if the density has converged, and then they see if the coefficients have converged. Okay. So you have many possibilities. And once everything has converged, of course, you get, we had 8, and you have computed the energy, and then you have 9. So then you can compute whatever properties you want from size. Okay. So that is the summary of the Hartree-Fock procedure. Then we will go back to the question we asked a little while ago. So is this optimized determinant psi 0 an eigenvector for some Hamiltonian? Is it? So let's do that. Let's try to see if it is. So consider the Hamiltonian, that is psi 0, an eigenvector of some Hamiltonian H0. Is it? Can anyone say, give an answer? Guess? I don't. Can anyone guess? Just guess yes or no.
Yes.
Yes, it is actually. Can you guess which one?
Ma'am, the Fock matrix is there now. The summation of Fock matrix, if you sum over Fock matrix, then it will, then that Hamiltonian will be the eigenvector of psi 0 will be of that Hamiltonian. I mean,
Yes, perfect. Yeah, that is the correct answer. So, if you have an H0, which is the sum of all the Fock matrices, then psi 0 is an eigenvector of this Hamiltonian. Okay. So can we try that out then and see if that is true? So let's do psi 0, and that is equal to so now I have to represent psi 0 as a Slater determinant. If you remember the shorthand notation that we had used, so this was it. So this was the Slater determinant representation. And if you think of, so let's take an example so that I can show it more explicitly. I have chi, A chi, B. Sorry, what am I doing? So if I apply F1, so here I'll use a different letter here because this is actually the number of electrons. The Fock operator is not labeled by spin orbital. This is labeled by no. Sorry. Very sorry. This is the F1 plus F2. So this is 8, 0. This acts on 5, 0. So you have 1 by root 2. F1 acting on chi A1. This epsilon A chi A chi B. This is from the first term. Then you have minus 1 by root 2. F1 acting on the second term. So that will give you epsilon B chi B chi A. You have again F2 acting on the first. So that is plus 1 by root 2. Epsilon B A chi B. Then the second one, so 1 by root 2. So F2 acts on chi A2. So you get epsilon A chi B chi A. So combining this and this, you get 1 by root 2 epsilon A and chi A chi B minus chi B chi A. The electron indices I have not written. That is, the first one is coordinate of 1, the second one is 2. Always. It's always 1 and it's always 2. It's always 1 and it's always 2. And then again you have another term which is epsilon B common and chi A chi B minus chi B chi A. So this is equal to 1 by root 2 epsilon A plus epsilon B chi A chi B minus chi B chi A. That is 1 by root 2 epsilon A. Epsilon A plus epsilon B and the determinant chi A. So I forgot. So yeah, so in Gauss the notation includes the 1 by root 2 factor, right? So remove that. That is this. So if my H0 is a sum of Fock operators of all the electrons, then I get And H0 psi 0 is equal to sum sum of the energies epsilon A equal to 1 to n psi 0. This is good. So does this make sense to you now? So I took an example of two electrons. So if you have electron 1 and 2 and you define a Hamiltonian, which is just the sum of the Fock operators of two electrons, then if you operate that on the wave function, then you get back the wave function and an eigenvalue, which is the sum of all the so-called orbital energies.
Hello, ma'am.
Yeah.
Uh, the index I equal to 1 to n epsilon I, that is index is I equal to 1 to n. That first line and second, that is summation of all the energy EA EV plus EC.
Yeah. Sum of all the energies of the orbitals. So all the orbitals in the determinant. So all the orbital energies in the determinant. So that is the answer of the Hartree-Fock equation. So you have the orbital energies here. Where is it? So in FC, it's the diagonals of the epsilon matrix. So let's see which one is easy to see. So it's this actually. All the orbital energies or the diagonals of this. This is your Eigen. So this is your Eigen. Why is it not writing? So this is the Eigenvalue matrix, and this only has diagonal elements. So every diagonal corresponds to the energy of the spin orbital. So each spin orbital, and the sum of all those diagonals, the trace of epsilon, basically. So this is basically trace of the epsilon matrix. So that is the eigenvalue of H naught. But you see, this is not the Hartree-Fock energy. So that is the main point here, that E0, that the expression of E0 is not simply the sum of the orbital energy. So what was E0? We wrote this before. So where did we write it? Here. So E0 is actually this. Okay. So this is in spatial orbital basis. If it was a spin orbital, you wouldn't have the 2. So you wouldn't have the 2 and the sum would be up to n. But even then it is not the same. Because what is the expression for each orbital energy? Let's look at that. Okay. Let's look at that. So each orbital energy is an expectation value of the Fock matrix with respect to A. And what is that? That is simply I have to write it. Open it out and write it. Right. So this is the expression for each orbital energy. But the total energy has a different factor. Just 1 minute. So I got a bit confused here. Just 1 minute. So yeah, so the thing is that the orbital energy is summed over all the other electrons. But the but the full Hamiltonian that contains a sum over all the electrons. So there is so if you take H minus F, you will get something that is not zero. So that something is basically It is what is called the uh, no, it's not really called something. So this, so the Fock potential has a name which is called V Hartree Fock, and the difference is not zero. So this is not equal to zero. So that is why there is a difference between H and H naught. So I'm sorry for getting confused at the end of the class, and we're also over time. So we'll start with this on Thursday, okay? And then we can complete the Hartree-Fock theory. And in between, I will increase the deadline for your assignment. And I will also give you the Hartree-Fock assignment, but I will give you an even longer deadline, so you will be able to finish it. Okay, so thank you. Yeah, and any questions?
Okay.
Yeah,
Hello.
yeah.
I tell you later. I have to check.
What?
I'll tell you later for the question. I some doubt.
Okay, sure, no problem. Okay, thank you.